The Lewis dot diagram is an extremely useful method of depicting how a compound appears, and it's essential that you know how to draw one. However, there are a few limitations with this model. Firstly, not every bond in chemistry is a full bond, an emphasis on the quotation marks around full. Oftentimes, we find that molecules contain not single or double bonds, but an in-between length, a 1.5 bond, for the purpose of giving it a name, although this of course does not exist. Obviously, a Lewis dot diagram is never going to show a bond of this nature. To overcome this, we introduce the idea of a resonance structure. Resonance is when more than one valid Lewis dot structure for a compound can be drawn by shifting around only electrons. It's important to take a moment to note that in resonance structures, only electrons are shifting around, not atoms. The reason for the existence of resonance is the same as the existence of bonds. It lowers the overall energy of the molecule, thus providing more stability. This comes as a result of the electrons being delocalized. If they're further apart from one another, their electron-to-electron repulsions decreases, and therefore the overall energy of the molecule also decreases. So, make sure you understand this. Resonance exists when we can draw more than one valid Lewis dot structure for a compound. For instance, say we were asked to draw the structure of carbonate, chemical formula CO3 2-. If you're looking at this with a blank mind and you have no clue what to do, or if you get confused when I start talking about formal charge later on in this video, I recommend checking out the video I have over drawing Lewis dot structures on my channel first before continuing with this one. I go in great depth over these topics in that video, so I recommend you check that out. As you can see, I've drawn this Lewis dot structure as accurately as I can. The formal charge for this upper oxygen is 6 minus 6, which equals 0. The formal charge for this carbon is 4 minus 4, which also equals 0. And the formal charge for these two lower oxygens is 7 minus 6, which is negative 1. Those aren't 0, but I can't do any better than this. What if I took the double bond we find up top, and I just removed it, and then drew it down here, adjusting electrons as needed? As you can see, the formal charges of each of these atoms is still as close to 0 as possible. The formal charge of this oxygen is negative 1. The formal charge of this oxygen is negative 1. The carbon is 0, and this oxygen is 0. They still have all the same formal charges, but the actual location of the double bond has changed. So which one of these drawings would be correct? The one with the double bond on top, or with the double bond in the bottom left? The answer? Not a single one of them. What you need to understand is that the only reason we make multiple of these Lewis dot diagrams is to show that multiple structures are possible for this compound. But what really is going on with the molecule? Some of the electrons are delocalized. This means that they are not confined to a single bond or atom. Instead, they are spread out or shared across 3 or more atoms throughout the whole structure. They belong to the molecule as a whole. We wouldn't just be able to point out a specific bond and say, the electrons are in this location, because they wouldn't be there. That's what's important for you to understand, and it's something that stumped myself for a while as well. We draw the resonance structures to show that the electrons are delocalized, but none of them accurately show where the electrons actually are. Again, you need to understand that with delocalization. To truly show where the electrons are, we'd need a different model than Lewis dot structures. You literally cannot show it with a Lewis dot diagram, and I really want you to drill this in your head. So how does the compound actually look? Each one of these bonds in the molecule carbonate will be shorter than a single bond, but not a single one of them will be as short as a double bond. The true structure that the molecule will take is what we call resonance hybrid. That's the structure which contains the actual correct length of bonds. We just physically can't draw this out in a Lewis dot structure, because it forces us to draw either single or double bonds. To quantitatively describe the length and strength of the bonds, we can use something called the bond order. It is very important you understand what this is, because we can use it to predict the actual existence of molecules, a topic which will be elaborated on in a future video. To find the bond order of a molecule, you take the number of bonding pairs of electrons, which is just a fancy way of saying the number of bonds we have, and we divide this value by the number of bond locations in the structure. That's just areas where bonds will exist. Doing this for the molecule carbonate, we would find that we have 4 bonding pairs of electrons. 1, 2, 3, 4. And we have 3 different locations where bonds will exist. 1, 2, 3. This gives us a final bond order of 1.33. Because this value is not a whole number, we know that resonance exists in this molecule. And we also know that because the value is 1.33, the average length and strength of the bonds falls between that of a single and double bond. The bond order also helps us to see how delocalized the electrons are, or whether resonance structures are likely to exist. When it's not a whole number, like in the case of carbonate, 1.33, it clearly indicates resonance. However, even if the bond order is a whole number, the molecule might still have resonance. What matters is whether multiple valid Lewis structures can be drawn that differ only in electron placement. So, just to summarize that into a rule you should memorize, if the bond order does not equal a whole number, then you know for sure that resonance structures will exist. If it does equal a whole number, you'd have to see if you can draw multiple valid Lewis structures. Moving on to the last part of the video, how can we portray resonance structures? Pretty much the same way I did for carbonate. We would need to draw out all possible Lewis dot structures for the model, as I've done below. Notice how I've also drawn a double-headed arrow connecting each structure. We do this to show that the different structures are contributing to the overall hybrid molecule, not flipping between one another. That's the last time I'll repeat it in this video, since I'm sure you're tired of my voice by now. But remember, not a single one of these drawings are correct, and the hybrid molecule is not just flipping between these structures. We literally cannot represent the actual hybrid structure with a Lewis dot diagram. This is the best that we can do. And that's all that you need to know about resonance. You should now be prepared to answer questions in either your chemistry class or on the AP exam, or even the IB exam if you're taking that, about resonance for molecules. The next video on my channel, VSEPR and hybridization, will further build on top of this. So if you're looking for more information, I'd go to that one next. I know that this was a lot of confusing information to take in at once, so if you feel confused about anything, try rewatching parts of the video. If it's still not making sense, take a break and come back later. Thank you for watching.